All right, welcome everybody. My name's Paul Adlaka with Secor, and we're here to present to you a fairly exciting project, ArcticX21. It's actually ongoing right now. We're sitting here in Odense, Denmark at the Hans Christian Andersen Airport, executing the project, and we're at day 2. We're just completing day 2 of the demonstration. We're going to have a few speakers in this session. Paul Curlett from Boeing is going to kick it off with who we are and what ArcticX is all about. Kim from NDSI is going to be more on the technical side, telling us what the system architecture is like, what is it that we have to offer. I'll go through a bit on the satellite side, what's the satellite focus for ArcticX, and how we've done so far. Rami from Lars is going to talk about some of the activity detection technology that they've got, and Melita from UDA is going to talk about the open source social media aspects of how that integrates into this solution. So, with no further ado, this is Paul Curlett from Boeing, and I'm going to step out of the picture and pass it over to Paul. Well, actually, I'm still in the picture. But
good afternoon, everyone. I'm Paul Curlett. I'm a senior analyst with the Boeing Company, and I've been assigned the Integrated Remote Sensing in the Arctic project. And in that project, I work with the URSA development group to pull together the activities responsible across a portfolio of several different countries that we're involved with under our offset program. So the IDG is an international collaboration of industrial partners and international industrial partners facilitated by Boeing through our International Strategic Partnership Organization. We actually individually selected these key companies because they offer key technologies and capabilities to allow us to fulfill this project of Arctic monitoring, which we think there's a huge need for in the future. The key objectives in this particular exercise that we're doing today, ArcticX, is to demonstrate these remote sensing capabilities. And I'll talk a little bit about it, or some of our team will talk a little bit more about some of the overview. But basically what it is, it's a system of systems solutions for remote sensing and communications in the Arctic. And the plan is to deliver it as a service through this IDG group. The solution will include satellites, aircraft, remotely controlled vehicles, a mission control center or a series of mission control centers that will provide data analytics, artificial intelligence, and situational awareness and common operating pictures to specific users who have requirements in that particular area. So it's really, today's about the remote sensing service aspect with the emphasis on satellite technology, since obviously we're talking with your group and that's the focus of today's agenda. The main IDG companies spearheading ArcticX are Mr. Paul Adlaka with Secor, the MDSI team that we have here with us, and then Andoya Space. We, with Boeing, work collaboratively to try to pull this all together. Let me speak a little bit about the roles of each of those individual companies. So Secor is the remote sensing lead, bringing in satellite data, ground station network, and analytics to the solution. So trying to build in AI to be able to identify some various different things like, dark targets or illegal fishing activities or trafficking activities that we want to highlight. MDSI, our Danish partners, bring together some military personnel and pilots who are responsible for systems integration, concepts of operation, and mission planning. Andoya Space actually brings in a wide range of things to include a space range and the capability to be able to do technology demonstrations that require secure and instrumented air and marine space operations. And then for us in the Boeing organization, we bring in a variety of assets into URSA and ArcticX, including through our subsidiaries that we used to have that are now integrated within the Boeing. We have platforms like Integrator, ScanEagle, Waveglider, various different platforms to be able to collect information. But then we also have a program called COM-C2GE Global Edition, which allows us to take those sensors and fuse those together and to provide that information through a thing we have called virtual range and a joint operating picture, so that we can provide to operational commanders or people who have specific missions visibility into what's happening, so they can have that as a capability to be able to drive their decisions on how they're going to react to some of those things. So our MDSI partners will provide a little bit more detail around what ArcticX is, what's happening right now, and then what we're executing, what we previously executed in phase 1, and then what we're going to execute in phase 2. Our phase 1 exercise, we actually had planned to have a exercise where we would all be in Norway, but because of COVID-19, we were not able to accomplish that. And then we actually executed it from Seattle, from Canada, from Norway, and from Denmark, with all of us participating virtually, but actually still being able to fuse all that information and do all those activities, with the mission center actually doing the command and control out of the Andoya Space Center. So it was a very, very highly successful event. But today we're now all together, all with each other, executing phase 2. And right now, from the activities that we've been doing with that, that's coming together really as a very important and very successful international effort and event. And the opportunity here is that we're going to have a lot of an opportunity for our customers to actually see that we're no longer into the theoretical or the PowerPoint, but we're actually into the demonstration of the capabilities that just came up on the slide. So again, Canada, you have remote sensing, satellites, ground stations, analytics. Denmark, campaign manager, scenario planning, network design, systems integration. Norway, you got test range, mission center. UAVs, we have a piloted vehicle, but we also, through Boeing, we have remotely piloted vehicles, and then campaign aircraft. And then eventually, obviously from us, from the Boeing perspective, we're providing vehicles, we're providing common operating picture, and we're providing this virtual range, which takes inputs across so many different activities that we can all integrate that in. We can take feeds like what's happening from the Maritime Patrol perspective, and people who are actually transmitting their position and where they're at. And if they go dark, we can see that and find that and be able to respond to it. We can pull down the ADS-B picture, which is all the air platforms that are operating in the spaces that we're interested in. Certainly, we can pull up things like weather. We can pull up things like various different informational activities that provide us information to be able to tell us what those targets look like, what we should be looking for to be able to help us do that. We also work in association with other companies that aren't core Planck members of the organization, but also contribute in some way, shape, or form, and you can see those on the bottom of the slide. So without further ado, I'm going to pass it off to Kim Nuskov, who's our MDSI counterpart, and I'll let him talk a little bit about what ArcticX is all about.
Yeah, hello everybody. My name is Kim Nuskov from MDSI in Denmark. We are running the systems design, so the design of the system of systems, setting up the requirements, and developing the capability from the PowerPoint to the demonstration we're doing here today. So what you see on the slide now is a set of our acquisition assets. So we're basically looking at utilizing satellite data for acquisition of, in this exercise, surface vessels. We are looking to provide situational awareness as a service using satellite acquisition, detecting using AI on the satellite data, and detecting vessels, screening them up against the AIS, and detecting those vessels that are not identifying themselves. We're also able to identify icebergs. We have a focus on the Arctic. The capability is going to be global, but we have an Arctic focus at the moment. So we can identify icebergs, but we can also identify oil spills, all using the same kind of data. We fuse this information into our command and control system, our mission network, where we are able to turn around and task airborne assets. Could be UAS systems that we have here, or manned assets, and fly out and identify those surface vessels that are not identifying themselves via AIS. This capability, next slide please, This capability has been in development over a few years. We started out in 2019 with the PowerPoint, with writing a concept for how this was going to be developed. We've written use cases for search and rescue, broadband communication, and all domain situational awareness. And with that, we started developing our set of requirements for the system of systems. Once we did that, we started writing a concept for how we're going to operate. What is our ISR collection plans? How is the mission center organized? What's its procedures? How are we tasking and planning our operations? With that, we also started doing modeling and simulation because we wanted to validate the design of the architecture that we had set up. We wanted to validate the requirements for what kind of assets we would need to provide these services. And with this modeling and simulation, we also stood up this virtual range that Boeing mentioned, or that Paul mentioned just a minute ago. The virtual range is a modeling and simulation capability that's also now entering into becoming a part of our command and control system. So we actually have a modeling and simulation capability implemented into our command and control, which is quite novel, I think. We are now moving into the concept demonstration. So over the last year, we have preparing this ArcticX activity, the first demonstration exercise where we're doing this for real. It's really successful. We are really, we are achieving the objectives we set ourselves out to achieve. We were hampered by COVID-19, so we planned the activity to be held in Andøya Space in northern Norway in August. But because of COVID, we were limited in who could participate in the exercise. So 2 months ago, we decided to do the same thing here in Denmark. So in a month and a half, we switched to Denmark and got the necessary approvals to fly UAS systems here as well. So it shows a bit of the agility we have in the system here. So yeah, you should come and have a look. Yeah.
Yes,
Yeah.
absolutely.
Yeah.
All right, thanks
Okay.
a lot, Kim. We're gonna move it back this way. So yeah, as the folks mentioned, we're sitting here in Odense. We're at the airport right now. There's racing cars going up and down the runway, but we just finished with some of the RPAS flights today and some of the aircraft flights. There's another flight going out now. This is the full demonstration. In Norway, we were only able to demonstrate the satellite system, some of the validation assets, and the command and control, the COM-C2G, we'll call it Common Operating Picture side of things. Now we've got the full system under demonstration. We're just completing day 2, partway through day 2, and we have 2 more days to go. This mouse isn't working. Let's try this one. So let me tell you a little bit about phase 1, and then we'll talk about what we're doing here in phase 2. So phase 1, we called it Ursa Light. So it's not the full system demonstration, but it's the system we could deploy into a hostile or a lockdown area, or a place where you don't want to have a large footprint, a human footprint on the ground. So it was satellite focused. We had several radar satellites, and you'll see the public missions there as well as the commercial missions. We had satellite AIS. We had some optical missions, mainly Sentinel-2, but we did have some optical satellites there. And of course, Exact Earth and Orbcom from the AIS. The analytics platform was on display, our CoreSite analytics platform. The Mission Control Center was operating. Common Operating Picture was operating. And then the assets we had is, if it's a satellite exercise, we needed the validation data to go along with it. We had everything from aircraft, the Diamond Aircraft 62 from Andøya. We had surface vessels out there, staging scenarios, and different types of information streams helping us validate the satellite data. So what we did was we turned ArcticX into an event-driven, scenario-driven event. So it's a demonstration of what we can do against specific scenarios. We came up with 3 scenarios: illegal fishing, illegal goods transfer, dark target shadowing. We also wanted to demonstrate the ship iceberg discrimination capability. There are no icebergs in August in Norway, so we brought forward some of the data that we used in the May-June timeframe off the east coast of Canada. And we were prepared to do an oil spill exercise and demonstration, but it was canceled due to weather. There will be several more of those that we'll be able to play with in the next little while. Show you some of the assets out of Andøya. These are the assets that went out and staged the scenarios, the illegal fishing scenarios. And you'll see that orange tape on there with the corner reflectors to make them more more visible, let's say, to the coarser resolution satellites, and very highly visible to the high resolution satellites. We also staged some social media events through Twitter, and Melita will talk a bit about those a little later. So give you an example, we modeled this scenario. It's the illegal fishing scenario, and what you'll see here is you'll see two ships up at the top left, a factory freezer and a trawler. The trawler takes off and goes into an illegal fishing zone, a closed fishing area, and starts fishing. And that green swath that you see there is the Sentinel-1 pass. The ship will go in, the trawler will go in and start fishing, and the green line back and forth is a ferry crossing area where there's people on board and they're tweeting what they see. The purple patches that you see there, that's the Capella satellite swath that we're tasking it to try to catch the trawler as it's moving. So this is all the data that we're collecting and then analyzing after the fact. Having the control over the waterways in Andoya and around Andoya, perfect area to stage these types of exercises. While that's going on, and every time there's a satellite pass, we've got the Diamond aircraft from Andoya flying overhead to validate what it sees against what the satellite sees. We had coastal radar, we had coastal AIS data, and of course our friends at Exactor, their AIS data, so we can validate what we're seeing from satellite against independent data sources. Operationally, what do we do? So here's an example from the first day of the exercise. This was a 8-day exercise. We had scenarios staged for 6 of those days, and on the weekends we went looking offshore to see what we could find. Here's the output from the CoreSite analytics platform, and what you see here, I know it's a little difficult. That red polygon is the area of interest where everything was staged. The white rectangle is, in this case, the Sentinel-1 footprint, and then the intersection of the two is where we analyze the data, and the green and the red pixels. The green are verified targets, so those are ships that are squawking. We can verify them against the AIS reports. The red pixels there are ships that are not reporting and need further investigation. And the tool will allow the client or the user at the other end to take a look at each of these pixels and say, I know what that is, I'm going to change the classification, or what is that, and bring up from the AIS database or some other database, marine.com, what is the exact ship that's there? Does it match what it's saying it is? Some of the highlights, there's a ton of data that came out of phase 1. We're still going through that, but some of the highlights is being able to see the same vessel in multiple images. And in this case, on the 18th, Sentinel-2, an optical image, we're seeing the vessel. A little while later, about 6 hours later, we're seeing it in Sentinel-1, and a couple hours after that, we're seeing it in the Capella image. And you can see the track on the kind of in the middle right-hand section of where that vessel was headed. Another highlight was being able to do some demonstrations around tactical tasking of these satellites. And in this case, it was the Capella satellite a couple of days later. We're picking up something in the RadarSat Constellation mission about 7 minutes later, we pick up the same target in the Sentinel-1 image. And then 3 hours later, we're picking it up on Capella. And then a couple of 4 hours later, we're picking it up in a second Capella. How we got those last 2 Capella images was basically pushing the order button and getting that down to about 75 minutes between pushing the order button and having that image acquired. That was excellent exercise for predicting where that ship was going to be and catching a high resolution image of that vessel. Some of the other, so we've shown how we were demonstrating the tactical tasking of the satellites. How quickly could you push the button and get an image? The second part of the exercise was, and we actually demonstrated this with our ground station in the iceberg detection season, was once an image is acquired, how quickly could you provide a product to a client, an analyzed product? And in this case, going back in June off the east coast of Canada, during the iceberg season, using our ground station in Happy Valley Goose Bay and bringing down TerraSAR data, we were bringing down TerraSAR data. Because we didn't have the TerraSAR processor in Happy Valley Goose Bay, we shipped the data to France to get it processed, brought it back to St. John's to do the analytics on it and do the target detection. That whole process from the time the image was acquired, bringing it down, shipping it over, back and out the door was 34 minutes. Could get that a lot quicker if we had hadn't had to ship the data back and forth, but in terms of a demonstration, extremely effective demonstration. The COMC2G, this was something that came together over the course of a Boeing development that came together very nicely over the course of the last 6 to 8 months, targeted towards this demonstration. And it's extremely unique. There's a lot going on in this slide, but what I want you to focus on is the green, and I'm not sure if you can see my cursor, but the green routing that's going on there. This is the route that's planned for the RPAS or the drone. And then the figure 8 there is the loiter for the drone once it reaches location. So what you're seeing here is the tactical planning tool side of the common operating picture. And then on the next screen over, right next to it, you can see it from a planning perspective, but you also see the situational awareness that the system's able to, in real time, bring up what's happening in the area with the assets, what are the ship tracks, what are the aircraft tracks, and take the analyzed satellite outputs, the dark targets from the satellite analytics, and put it into the situational awareness picture. So you have both the tasking side of things and the planning side and the actual situational awareness. So that's a highly successful demonstration because this is the same display that's happening in Norway, happening in Denmark, and happening in Canada at the same time, sharing that amongst the folks, especially. Pardon?
In Seattle.
And in Seattle, that's a good point, yeah. So especially when you've got analytics happening remotely, from the mission planning happening remotely, from where the assets are being deployed, an excellent tool. So we're sitting here right now in Denmark. We're in the middle of phase 2, and we're able to demonstrate the full URSA solution. The red area that you see is the area of interest. That's our test area, predominantly on the western side of that. We're focused in on there, and we're adding some aircraft, and we're adding the in situ RPAS, Boeing in situ RPAS, the Scan Eagle with a visual LiDAR type of a sensor, the integrator with electro-optical, high-res electro-optical, and a SAR sensor. And the integrator ER is the extended range platform that in situ is operating from here at the mission center in Denmark.
Right now.
Right now, it's going on right now. Yes, I wish we could show you that, folks. But the plane is at the RPAS is actually flying out of Oregon. So you've got people here flying the plane in Oregon, which is an incredible demonstration. The satellite assets, we've also juiced up the satellites that we're using this time around. And what you see here, it's actually a one-day demonstration, one-day simulation of all the satellites that we're using. But when you take a look at the radar satellites, we've brought in addition to the freely available data, a bunch of the new innovative systems like the Capella, like ISI, and Galfin, which is a new satellite that we've just started using. We've also brought in a lot of optical satellites, the Satellogic, brand new system, the SuperViews, and Maxar's WorldView satellites. And that's in addition to the Exactor satellites. And what you see here over the course of the day is there are gaps during the day, but they're not very big gaps. We're now collecting data at significant slices during the day. And just to give you a sense of that, this is a little bit of a busy graph, and it doesn't have all the satellites on there. But that box that you see with all the dots, that's a 24-hour slice of the test. Each one of those columns is about 3 hours. So, and you can see there's not too many 3-hour periods where there aren't a lot of those dots, which are satellite acquisitions. The listing on the left is about half the satellites. But we're using 47 satellites across 11 different missions in this exercise. A lot of data coming in around target detection. So a lot of work going into the target detection side of things, which is what we're doing when the satellite pass takes place. The next layer of this whole maritime surveillance campaign is looking at what happens between the satellites passes and what's the activity detection look like. And that's where our partners come in. I'll start with, we're focused on Exactor data for a reason. And you can see from this particular slide, the light blue is very dense coverage. The coverage of Exactor over the two other competitors in the Arctic is phenomenal. That's a blanketed over the Arctic. And it's real-time access to the data, which is critical for us. We take that data, we work with one of our partners, Merospace, to take all, if you look at that left-hand picture, That's at a snapshot in time. What are all the reports? And some of those reports are 8 hours old. Some of them are 6 hours old, but there's a huge cluster of reports. They'll take all that data, filter it down, and get it to exactly the time and predict the location of those targets at the time of the satellite pass. We need that to be able to do our dark target detection more effectively. So there's a strong partner in there with Aerospace. And I think before I get myself into trouble, I'm going to turn this over to Rami. And Rami, are you able to speak to this? And I can advance the slide to you, but this is about the activity detection portion.
Yes, of course. Do you hear me, Paul?
I hear you fine. I'm going to mute.
Excellent. Yeah, perfect. Thank you. So thanks for that. So what we wanted to kind of demonstrate here is we've got a couple of engines here. What you're looking at is the output of what we call Total Insight, our big data analytics decision support system that has 5 layers of data analytics. And the back end is all driven by artificial intelligence and machine learning, where we have learned the patterns of life for various kind of anomalies. There's multiple layers that we process. Obviously, fusion and track correlation is one, but anomaly detection, as you're seeing here, is another. There's also threat assessment. There's predictive kind of services, and we go up in layers. So that's kind of layer 2. Layer 3, we're getting into kind of impact assessment, where we're generating kind of course of actions straight out of machine learning. And then layer 4 is more mission planning, flight planning, and response planning, where we try to generate, using modeling and simulation and multi-objective optimization, kind of a better way of solving or responding to a particular situation in the future for that particular deployment. So here what you see is one of those anomalies. We have about 20 in the system. This is a blue water rendezvous. I don't know, Paul, if you can actually click on that left screen there, if the video will actually play out or not, but yeah, right into the screen itself, into the Google Earth screen itself. Yes. Oh, yeah, it looks like it's playing out. So there's Total Insight kind of processes trillions of messages per day and kind of looks for those patterns of life that we've learned or that it's learned using machine learning. So here's kind of 2 vessels that are, you can see them right there. They're rendezvousing about 450 kilometers northwest of Vancouver Island. They move together for about 125 kilometers east, and then they leave in separate directions, as you see there. Everything is captured in our backend knowledge base so that we can perform things like retroactive analytics and diagnostic and descriptive analytics. In this particular case, it's 2 fishing vessels. This is probably a very benign rendezvous, but again, did they take out a license to perform that operation in those waters and so on and so forth? So there's still some other data sources that could be fed in that could create a particular risk on the environment or a risk from the environment upon the actual vessels themselves. The anomaly here triggered with a confidence of 0.88. What that means is our machine learning models provided us with a very high confidence that this is a particular rendezvous that met all the patterns of life that the machine learning algorithms and models learned during training and that are now being inferred in the real world. Next slide. Hit next. Yeah, there we go. So another typical kind of pattern of life is bunkering. So we'll catch these a lot, or Total Insight will catch these a lot. Again, if someone can click in the middle of that Google Earth window, there should be kind of a video that plays out. Yeah, so we're receiving trillions of messages per day. We can process things like space-based AIS, littoral AIS, LRIT, GMTI, even on the surface, radars, all kinds of radars, including synthetic aperture radar-based detections and Doppler radar, and a few of the other radar modalities. Open source intelligence could be brought in as well, so that we can have a higher confidence detection on the anomaly itself. So in here, you can see the 2 vessels kind of bunkering together off of the coast of Angola. They maintain a parallel course for about 10 kilometers. They maintain a distance of less than 40 meters for about 5 hours and a speed of less than 1 knot for those 5 hours themselves. So obviously a bunkering activity. Again, was there a license that was taken out? Not every single rendezvous is suspicious. There could be completely benign ones, but can we explain them? And the ones that are completely unexplained are the ones that are probably the ones worth investigating by stakeholders and security organizations. This is just rendezvous. There's unexplained high speed, unexplained low speed, and unusual course shape, irregular track summary, dark targets, invisible targets. The list goes on and on that are all driven by artificial intelligence and machine learning that Total Insight can spit out in real time. And of course, we can play them back in CoreSite Analytics or any other kind of visualization system. Here, we just show you Google Earth, but we've interfaced to many such systems, including CoreSite Analytics. There's other layers as well as other suites, including modeling simulation, multi-objective optimization, so that we can, once an anomaly has been detected or once a threat, a high-level threat has been assessed, we can automatically, using AI, generate response planning. Paul talked about the assets that are in play here. We can generate automatically AI-driven response plans or flight plans or mission plans in order to minimize that gap duration that he talked about and demonstrated on the SAT side, but taking in multi-domain operations at the same end. Anyway, those are kind of my 2-3 minutes. We're from Layers Technologies. Very happy to participate in this. And Paul, the floor is back yours.
Wow, thanks a lot, Rami. That let me put that video back on. I'm not sure. Yeah, okay, there it goes. Yeah, thanks a lot for that. We covered a lot of ground in a very short period of time, but that was good. All right, so the next slide is more on the data fusion and analytics using open source intelligence and open source data. And UDA Technologies is working with us on this. And Melita, I wonder if I can get you to take it over from here and speak to the next couple of slides. We are way ahead of time, so folks, we're good to take our time with this. Thanks.
Okay, great. Thank you. Thank you for inviting us here too. As I'm happy actually to confirm that we are also in data fusion business, like all of you seems to be, and in some of us date from like Lockheed Martin to like design data fusion system for Halifax class frigates. Here in UDA, we have this cloud-based architecture infrastructure that is actually able to ingest any kind of either hard or soft data and process it and fuse and make reasoning about whatever it's necessary, including maritime anomaly detection. You have mentioned that aerospace, I mean, it's great to have a big coverage and actually extensive coverage or satellite coverage. However, I mean, even in the SAR, I mean, if the weather is bad, you can not really, if you have an optical sensor, you cannot really observe what's going on there, or SAR image sometimes can speckle noise can hide the small vessels. And we know, like in wanting to detect dark targets, the people who don't collaborate, do not use their AIS transponders or antennas. So with proliferation of mobile technologies, I mean, we were motivated to tap actually in open source data processing, which we have demonstrated so far in space deterrence projects, in military intelligence projects, and most recently in COVID project related to detect the outbreaks from all kinds of documents, news documents, scientific reports, as well as social media. In the context of Andoya, for instance, trial, we had situations where some of the satellites have not detected the really small vessels, and neither, I mean, they did have AIS on. So in that case, we had several Twitter messages that were able, with linguistic content, which our tools, deep learning tools, were able to extract the information and put that detection of a vessel there. Namely, we have this open source information extraction and analysis and reasoning tool, which actually extracts actionable intel from open source data and estimates states from situations through fusion of data. Now, if there are many data, like there are different kinds of data, they can all be integrated. However, the pipeline that is used, for instance, here in maritime, in Arena's case, for Andoya and for Denmark, focuses on Twitter, source open data sources such as Farquhar or ship spotting. Apart
I'm sorry, Melita. I think you're breaking up. Maybe if maybe
yeah.
stop video.
Yes, sure. Okay. Is it better? Is this better? Do you hear me now?
Yeah, thank you.
Okay. So for the whole process, as I said, I mean, we have AI's data. Because they can come from various sources. Let's say we have two providers. You have to clean them, even if there are some errors in MMSIs. Knows that very well. Remove duplicate messages. Then the very important part is actually the fusion of all kinds of data that takes into account both kinematic and static and information and all kinds of attributes.
Sorry, Melita. I think we're losing you.
Realize machine learning
Melita.
can be good really when there a lot of data is to have
I think we're losing you again, Melita.
Okay.
I wonder if there's another way to finish this.
Is it better now? Okay. Hello.
No, I'm sorry.
Do you hear me now?
Yes.
Okay.
Okay. Okay. So I'll wrap this up. In any case, here we're able to, particularly for Andoya, we were able to detect dark vessels and illegal fishing activities due to analysis of open source data such as Twitter. And now for Denmark, we are also looking into Farquhar and ship spotting, which are blog-based open source data sources. If you can pass just to the next slide and video, Paul, please. Paul, okay, perfect. So this is just one of our older UIs showing an AIS computed a track, which is AIS and polar epsilon, that is SAR detection fused with Twitter message. Here, by the way, the Twitter messages can be either self-reporting or observational. That is, one can tweet from a vessel and that content can be associated with its own track, or one can sit on the shore or a ferry and see something going on, and that's an observational, and post it, and our system would then analyze and extract information from the linguistic content or picture and potentially fuse that information and that detection with the other available detections to contribute to the track. The tracking algorithms also can do prediction, of course, and let's say that would be all for now from our side. Thank you.
Wonderful. Thank you. Thank you very much, Melita. And sorry about the bandwidth problems.
Yeah, there was something, yes, a little bit of bandwidth, but I hope the message got through.
Yep, it's definitely one of the more interesting parts of the exercise. How is social media and how's all this open source data going to support the fusion of all the data and help detect activity, self-reporting or observational? Yes. So with that, I think, yeah, let me see. I wanted to put this up so you make sure that that everybody had the email addresses in case you did have any questions. But maybe, Sabrina, now would be a good time to just pause and see if there are any questions, and more than happy to take them.